полный зал. Начинаем. Следующий доклад. Профессор доктор Хасингер, директор Астрономического института университета Гавайи.
Yes. Thank you very much. Thank you to the organizers for inviting me, and it's a great pleasure to be back here at WIKI. I have, at least in the past years, I have come here very often, but in the past few years, I was not able to come. So I have to translate the title of my talk to understand it, to talk about the future features of the Hawaiian observatories and also the prospects for cooperation. And I'm very glad that indeed we have started already a cooperation between the Russian group and the Hawaiian group for the preparation of Eorosita science. But before we do that, I would like to give you a more broad overview of the telescopes that we have in Hawaii. This is Mauna Kea as a unit from the space station. And when you look at it from the space station, you don't really see the telescopes very well. If you zoom in a little bit, then you see a little ring of telescopes here. And this is actually the observatory on the top of Mauna Kea, where we have 12 telescopes on the top, and then there's a radio telescope a little bit further down. And just to do a little bit of advertisement, the telescopes up here are among the top producers in terms of scientific output. This is a chart that shows all telescopes larger than 3.5 meters in the world. And the bars are something like the luminosity, the paper output multiplied by some kind of impact factor per telescope. And the 5 or so most efficient telescopes of the world are on Mauna Kea, and the others are also on the left half of the plot. So we are very proud about the scientific output that comes from the mountain. And as you know, we are still fighting for building the 30-meter telescope on Hawaii. Also, it's getting more and more difficult, but I'm hopelessly optimistic that we will be able to build it, and so this will then add another powerful instrument to our observatory. Now, I want to make one point, because Hawaii is in the middle of the Pacific, and you know the Pacific is basically the half of the Earth which is almost empty. And this is actually specific reasons why Hawaii is such a great observatory, because on one hand, the wind is always blowing in a very constant laminar fashion, and the Hawaiian volcanoes have a very smooth slope, very gentle slope. They are very high, but the wind is actually blowing over them in a laminar fashion, and so the stars are not twinkling up on the summit of Hawaii. And that's the reason why every telescope that you put there is more powerful than when you put it somewhere else. And another point I want to make is that the direction, the distance to most of our partners is almost the same. We are sitting in the middle of the Pacific. And so what I would like to call this is a pan-Pacific observatory, because in the meantime, we have a great interest from the Far East Asian countries, Japan, China, Taiwan, Korea. We also have partnerships with Chile, Argentina, and Brazil. And then USA and Canada. And there is in principle a potential, and this is our collaboration with Russia. Russia is also a Pacific Rim state, and so it would be natural to think about partnerships between Russia and Hawaii in the view of this Pacific Rim. The total output, as I said, of telescopes on Mauna Kea is quite impressive. Here, this is the comparison of the Mauna Kea telescopes with, for instance, the Hubble Space Telescope and all ESO telescopes, and so we are in good partnership. We are actually dominating the world scientific output in astronomy from Mauna Kea. Now, just to give you a little bit of a feeling, this is a time-lapse movie of a few minutes of observations on Mauna Kea. Here you see the 2 Keck telescopes and Subaru and Gemini observing all the galactic center at the same time with their laser beams. And then you see how the night is moving on. Not always they are looking all in the same direction. Here you see the laser beams shining in different directions. And all the telescopes are active every night throughout the whole year, as long as it is not bad weather. Like, for instance, today they are observing right now Also, it has snowed yesterday, so they are still trying to get out everything. And so let me just focus on a few of the important telescopes that we are in particular planning to use for the eROSITA cooperation. You know that two Keck telescopes are the most powerful telescopes in the world, and in particular with their 10-meter sized mirror, they have a very large collecting area, but they also have a huge efficiency and a wonderful suite of instruments. And I would like to focus in particular on one instrument, which is MOSFIRE. This is the most sensitive near-infrared multi-object spectrograph, which is actually used for a lot of the exploration of the early universe. And so this will be very important when we want to follow up high redshift clusters like the ones that Alexis Finogenov was talking about today. Then the Subaru telescope is very important for us. The Subaru telescope right now has the hypersubprime-cum spectrograph. In the hypersubprime-cum spectrograph, you can imagine this almost like a telephoto lens in your camera, only 20 times or 30 times bigger. So this is a live person here, a Japanese person, 1.50 meters. And this is about 2.5 meters spectrograph. And the CCD focal plane contains 120 individual CCDs, and this combination is the largest grasped telescope, so that means the effective area of the mirror multiplied by the field of view. The field of view is 2 square degrees, and so this is the most powerful wide field imager on the world right now. And we are using this, we have been using it for our eROSITA preparation, as I will show you. In the future, the Japanese are building a multi-object spectrograph, fiber-fed, which can use this whole field of view. This is called the prime focus spectrograph. This is done in collaboration with Princeton and others. And so in the future we will also be able to use that prime focus spectrograph for the follow-up of eROSITA sources. And then the Gemini North telescope, we have so far, I personally have so far not observed on Gemini North, but it's clearly a very powerful resource. And then we are also using the Canada-France-Hawaii telescope. Canada-France-Hawaii means that Hawaii is actually a co-owner. We own about 15% of the telescope, and we are also getting roughly 15% of the observing time. And the CFHT right now, for our purpose, is a very important instrument because it has the most efficient U-band filter in the world. So if you want to do deep U-band surveys, you have to go to the CFHT, and so that's what we are using. And then there are 2 more telescopes which have belonged to the United Kingdom, the United Kingdom Infrared Telescope and the JCMT, the James Clerk Maxwell Telescope. Both of these telescopes have in the meantime been transferred from the United Kingdom to the University of Hawaii. So we are now the owners of those telescopes.
They belong now to you.
Yes, the ownership, they have stayed in Hawaii, but the ownership has been transferred to the University of Hawaii. And for the UCURT telescope in particular, there is something, we are operating that in partnership with universities like Arizona and also other partners. And we are actually looking for more partners. So if the Russian community would be interested in joining operations on UCURT, this is actually a very efficient and cheap way to get access to a 4-meter telescope in a major fashion. So this is something that I would like for you to consider. Another possible interesting possibility maybe in the long run, if Russia is really interested in the large generation of telescopes, it would also be a possibility to consider to join the TMT. So that will clearly be some interesting possibilities. Okay, and then this is not all. We have another mountain on another island. This was Mauna Kea on the Big Island. Maui is another island with a volcano that is not 14,000 feet, but only 10,000 feet, so about 3 kilometers high. And it contains some of the best observatories for instance, daylight observations. This is the picture of the Haleakala Observatory. There is a whole military complex which we call the Maui Space Surveillance Complex, where the Air Force is actually looking in particular for satellites. We are the westernmost point of the United States, and so it's clear that things that come from Far East would be interested to watch from here. But we also have civil access to some of these telescopes, so we can also use them. About 10% of this big telescope we can also use for real astronomy. And then on this side we have the new Daniel K. Inouye Solar Telescope, which is a national telescope which is just being completed. It will have first light, I think, in 2018. And then we have the two Pan-STARRS telescopes, where I would like to focus a little bit more. These are two small telescopes, 1.8 meter in diameter, but they have the largest optical cameras in the world. So this is actually one of the Pan-STARRS cameras. It has 64 chips, and these 64 chips together have 1.5 gigapixels. And so as such, until the LSST camera is finished, it is actually the largest camera in the world with a field of view of 7 square degrees. And so Pan-STARRS, just 2 days ago, has made us a great present. It has finally published the Pan-STARRS Sky Survey, which is about 3 billion separate objects and 2 petabytes of data. You can imagine when you would if you like to print out this data on normal A4 sheets, you need 47 million file cabinets to print this data. So we never print this data, but this is now available to the public. And this is an extremely important resource, I believe, for eROSITA, because finally we have the dream of an all-sky digital survey which is available for us. It's actually not all sky, the southern sky is missing, but it goes down to minus 30 degrees. And so, in the context of what Peter told us, the sky distribution between Russia and Germany, this is roughly where it cuts through. This is the galactic plane, the galactic center is down here, and so this is the Russian part of the sky, which is almost completely in the in the Pan-STARRS map, and this is the German part of the sky, which is also, I think, 2/3 of it is in the Pan-STARRS map. So I think this will be a very important resource. And so I just want to give you a feeling about what the huge amount of information which is in this data set. So I'm zooming into the galactic center region, that's this region here, and I'm zooming in a little bit further even. This looks roughly how our plates over lunch look like after eating the goulash. And so when you are now, it looks a little bit fuzzy, but when you are concentrating here, this is just one single field of view of Pan-STARRS. And when you zoom out, when you zoom in, then you see the galactic nebula and you see a lot of objects. So there's a huge amount of information and data that would be readily available for us. Okay, and that brings me to the scientific part. My main motivation originally, and this goes back to Abrixas, and then it goes back to the early times of Rosita, and then finally eROSITA, is still to try to understand the growth and the evolution of black holes. And you know that we have the active galactic nuclei, we have different variants. We have active galactic nuclei where we can see the center, and then others that are heavily obscured. And so with ROSAT, we were able to resolve only the ones that you can see directly. And then with Chandra and XMM Newton, we got the ones which have a moderate obscuration. But there is still a large uncertainty of what happens in the very hard X-ray band where only NuSTAR and in the future ART-XC can observe. Because although this model is now quite established and very, I think, popular, it still contains a large uncertainty about how many objects are obscured as a function of redshift. So the obscuration factor as a function of redshift is a very important ingredient, which could in the end actually establish how the AGN have formed at high redshift. And this is basically where Spectrum X Gamma with eROSITA and ART-XC will cover the whole band, and we will get a large number of new objects. So this plot has already been shown by Peter Predel. This is the survey sensitivity of eROSITA for point sources and for clusters. And so here, when you compare it with the ROSAT All-Sky survey for clusters, we are more than 2 orders of magnitude deeper here. And with for point sources, it's about the factor of 25, 30 that we were talking about. And And so this is what we want to exploit, this new parameter space. The log n log s of HEN is very well known, and E rho zeta will not go the deepest. I mean, the deepest will be done by the Chandra deep fields, but E rho zeta will cover a very important range from the first survey after 1 year. This is called E rho zeta 1, when basically the first sky survey has been done, and then until the deepest regions that are covered in the ecliptic poles. You span an order of magnitude in sensitivity, which is very important for calculating luminosity functions. And in the hard band, this is the blue data, and in the soft band, it's the yellow data. And so I'm particularly interested, and I would like to propose for cooperative work, one survey which is similar to what we have done in the ROSA times, where we work together with the Selejchuk Observatory to identify the 2,000 brightest sources in the ROSA sky, which gives a very important local anchor of the population. And then also we have embarked on the HEROES program. This is the so-called Hawaii E rho zeta ecliptic pole survey, where we are covering the deep north ecliptic pole with deep optical observations, and later would like to do spectroscopy. And so this is the current state of affairs with all the AGN that we know in the sky, in the hard band. This is based on swift butt observations, ASCA observations, XMM Newton, Chandra, and so on. And the Chandra deep surveys are covering the faintest and highest redshift population. But you see that there are big holes here. That is because there is no all-sky survey in the hard band. And this will actually be filled completely with E rho zeta over the 4-year survey. And the two surveys that I was talking about, the E rho zeta bright survey, which could in principle already be done after half a year. So this is something that could be done quickly as a very fast, because also the objects will be relatively bright, so that will be a fast turnaround identification program. And then finally, HEROES will cover the faintest part close to the XMM Newton and Chandra deep field surveys. We will get an even better characterization of the evolution of the AGN luminosity function. This is from our most recent work, Miyagi et al., and something similar has been done with Ueda, where you see the space density of active galactic nuclei, how they actually change with redshift. The most luminous AGN are peaking at a redshift around 2 to 3, and the least luminous AGN are peaking at a redshift around 0.5 or so. And so there's a clear trend of the peak going down to lower redshifts, which we call the anti-hierarchical scenario, because small things usually should come first, but in here the big things are coming first. But there's an interesting, when you look at this curve, there's an interesting other interpretation that you actually have two different modes of growth. You have one high luminosity mode, which is shown here, and then at lower redshift there's a lower luminosity mode, and this could actually be referred to two different accretion modes, one from major mergers, where two galaxies are eating each other up, and then from secular processes where pre-existing black holes are already fed back. So E rho zeta will produce a huge amount of additional information, in particular at high redshift, and then also will increase the statistics for lower luminosities, and it will be a very powerful tool for AGN work. But as you know, the most important work for E rho zeta will be the clusters of galaxies, and so that is where I have already started to do a bit more work for preparation. This is the exposure map expected for E rho zeta, where you get the deep exposure at the poles, and at the poles you are getting roughly 20 kiloseconds or something like that, and roughly above 10 kiloseconds E rho zeta will start to be confusion limited, and so the poles itself will actually be a very powerful deep survey. And so we have embarked this year on this Hawaii E rho zeta ecliptic pole survey, where the blue curve is 17 kiloseconds observation, the red curve is 15 kiloseconds observations, and the area in the sky that we are observing is visible from June to August roughly, so during the summer months we are observing those fields. I don't want to dwell on this too much, but we are observing those fields in 9 different filters, GRIZY and 2 narrowband filters from Subaru, and then we get the J-band in the near-infrared and the U-band with CFHT. And so the data, the first analysis of the data, which I have done personally myself, I was only able to look at the central field out of the 30 fields that we have. So we have now piped the data into the Pan-STARRS pipeline because it's just too much to analyze on your own. But the data is beautiful. As you will see, the resolution of the images is great. This is the G-band appearing in blue. And just by chance, the North Ecliptic Pole is very close to a planetary nebula, which is a fascinating object that for some people is interesting. For us, it is only a kind of foreground object. What we are mainly interested in are potentially high redshift clusters. So this is a group of galaxies with a relatively red color. And this is where we would like to follow up with E-Rosita and with X-ray observations. The seeing that we got was excellent. We got a median seeing of about 0.6 arc seconds, both on CFHT and Subaru. So 90% of the data that we are using has a seeing of better than 1 arc second, which is really excellent. And the number counts that we are getting are perfect in agreement with what we are expecting. So this is the GRIZYNJU band. And so the deepest fields that we have a limiting magnitude of 26 roughly, which is really wonderful. And the least sensitive band is the J band, the near infrared band that goes to about 22nd magnitude. So I think most of the E-Rosita counterparts will actually be covered by those magnitudes. And this gives a color diagram for the optical astronomers among you, where you can actually get a lot of information from excellent colors. This is actually an example from the Cosmos field, which is even substantially deeper. And we have a full set of photometric redshifts for all objects. And so this just gives you an example where you can actually see the stars here. This is the the K minus Z band, so C minus K, and this is the G minus C band. So these are relatively broad color ranges. And what you also see for the first time, I have seen that with naked eye, is the red sequence of the clusters up to a redshift of 1 roughly, where you can actually really see in the full field by displacing the colors the red sequence of the cluster. So when you select these objects, you can directly zoom into the clusters. This is our HEROES, the current status of the HEROES field, and we are still far from the accurate photometry that we need in order to separate it out. But I have done some tests. I think we also see the red sequence here. And so I have selected a few objects in this red sequence part, which is going roughly from redshift 0 to redshift 1 here. And these are a few candidates that I analyzed just yesterday. So this is going while we are speaking. These are a few cluster candidates, redshift 0.7, 0.8, 0.9-ish, where you can beautifully see and disentangle the different colors. I have not yet been able to push through the redshift 1 band. And what we are planning to do now, I mean, while we wait for E-Rosita to come, what I would like to do is, I would like to reanalyze the ROSAT data around the North Ecliptic Pole, because ROSAT has done the All-Sky survey, but ROSAT has also done a number of pointed observations. So this is just a quick look data of ROSAT for the central region. This is the North Ecliptic Pole itself. And so we would like to reanalyze the ROSAT data with a finer point spread function, and then we want to look up the optically selected clusters and see what their X-ray fluxes are. And so you don't need many X-ray photons to determine the flux. You need many X-ray photons to get the size of the cluster. So we can already do some preliminary work on ROSAT. I'm almost done. We are also very interested with the narrowband filters in finding high redshift Lyman alpha emitters. These are two examples from the Cosmos field, which is already based on our narrowband data. And this is one example in our HEROES field where there is one object that has a very bright red color. And so it's probably a Lyman alpha line at a redshift of 5.7. So we will get the whole emission of the Lyman alpha emitters over the 120 square degrees, both in the redshift 5.7 and also a 6.5 band. And then finally, that ties back to one of the talks that we heard, I think yesterday or this morning, about the gravitational lensing. We are also trying to find new lenses like this beautiful golden lens where you see an Einstein ring. And the large area that we are covering and the relatively good angular resolution of our images should allow it to detect a few of these golden lenses. Our Japanese friends have already found one golden lens where they have two Einstein rings at two different redshifts, so that's a very rare phenomenon. And so I believe we should have the data to get a handful, maybe 10 or so additional golden lenses in the HEROES program. And with this I would like to thank you. Mahalo is the Hawaiian word for thank you. Mahalo. And this is actually a picture taken a few days ago from Mauna Kea in snow. Somebody went up there because the road was closed, so they had to walk up there, took this photograph, and for us and in Germany we will have Christmas holidays soon, and for you, you will have it a few days later, so happy holidays to all of you. Thank you.
Well, you mentioned this briefly, but what is the future of the TMT in your opinion?
Yes, so the TMT is right now going through this so-called contested case, which is basically a kind of judiciary mitigation or measure of trying to listen to the community. This is dragged out right now by the opponents for a very long time. They try to postpone the decision because TMT has said that they need a decision very soon whether they will build in Hawaii or at the Canary Islands.
What is the deadline?
And they are posing a deadline by roughly September 2017 where they have to have the final decision. And I'm still very optimistic, I'm hopelessly optimistic that we will actually make that deadline. And so we are very strongly putting all of our energy in keeping the TMT in Hawaii. On the other hand, I mean, I understand the project, they need, the partners, they need an alternative site, and so Canary Islands is a site, but it's definitely not as good as Mauna Kea.
So you selected J-band also for this survey.
Yes.
Can you explain why?
The J-band is more, because this is such a wide field, and the J-band is about twice more efficient than the K-band. So we would need twice longer to observe it with the K-band. Maybe we can come back later and observe it with the K-band as well. But the CF...
What do you mean more efficient? Is that specific of U-curve?
No, this is actually with CFHT. In order to reach the same sensitivity with the K filter, we would actually have to expose twice as long. And so right now it's a kind of compromise between covering a large area and getting the sensitivity. And the problem is that CFHT is actually the most heavily oversubscribed telescope right now. And so while we march along with Subaru, unfortunately we didn't get the observing time for the near infrared for this year. So this is a very limited resource, and we have to kind of optimize it.
Лидия Михайловна, вы хотели что-то? Нет? Нет, ага.
Yes.
On your first slide, I've seen that CFHT gives more publication than VLT. Is it true?
Yes.
Slide number 3.
Yes. This is actually normalized by telescope. So this is per telescope. So that means the VLT you have to multiply that by 3.
Divided by 4.
By 4. And the KEC you have to multiply by 2. Sorry. But oops. But per telescope, this is KEC, this is UCURT, and this is CFHT. Okay, VLT you have to multiply by 4, so it's way out. And KEC you have to multiply by 2. But per telescope. Yeah.
Everybody is introducing its own.
Yeah, but this is Crabtree, who is a neutral person somewhere in Canada, so this is not our own. Yes.
Еще вопросы? Так, поблагодарим.